What we've done so far is partitioned an interval into several rectangles, whether they be non-uniform or uniform, and each rectangle has a width delta xi, and we multiply this by the value of the function at xi, which depends on which method we used, such as the left, right and midpoint Riemann sum. Now if we take the limit, as the width of the largest partition tends to 0, or where the number of rectangles we use tends to infinity, so in the limit, the width of each rectangle becomes infinitely small. So that becomes dx, and then we multiply this by the value of the function f of x, which gives the area of the infinitely thin rectangle, and then we integrate from a to b. And that is basically summing up the areas of all these rectangles from a to b. And this here is what we call the definite integral, which gives us the exact value of the area under a curve in the closed interval from a to b. Now you may be given a definite integral and then be asked to translate it into a Riemann sum. And here we'll illustrate the process using a left Riemann sum. So what we do first is partition a domain over some number of rectangles. And the width of each rectangle is b minus a on a number of rectangles. And then we sum the areas of each rectangle from some I value to n or n minus 1, depending on which method we use. Now using the left Riemann sum, we want to multiply the width of each rectangle by the value of the function on the left of each rectangle. So we have f of a plus the width of each rectangle, which is b minus a on n, and multiply that by the index I. So for the left Riemann sum, we initially want I equals 0, and then sum to I equals n minus 1. And you can see that when I equals 0, we get f of a, and then multiplying by the width of each rectangle gives us this area. And then when I equals 1, we basically evaluate the function at a plus the width of each rectangle. So therefore we're now taking this as the height of our rectangle. And then multiply by the width gives the area again. And then try to visualize this when I equals 2. So this basically gives us the approximation to the area under the curve using the left Riemann sum. And you can follow similar logic when you're asked to translate the definite integral to a right Riemann sum, and so on. Demonstrate your understanding of the definite integral using the diagrams below and the left Riemann sum. So for the left Riemann sum, we have the height of the left of each rectangle being f of xi, and the width of each rectangle being delta xi. And then multiplying them together gives the area of one rectangle, and then summing through over all the rectangles gives the approximation for the area. Now if we keep decreasing the width of each rectangle, so in other words in the limit, as the number of rectangles become infinity, and we're taking the limit of the left Riemann sum, well delta xi is going to approach 0. So this is the same thing as taking the limit as delta xi approaches 0. So we end up with rectangles of infinitesimal width dx, and the height's simply going to be f of x. And therefore we can write this sum as the integral of f of x with respect to x, which gives the area of that infinitesimal rectangle, and we're integrating from a to b. Let's translate this definite integral to a right Riemann sum. So recall with the right Riemann sum, the right of each rectangle touches the curve. And we'll assume rectangular partitions with a uniform width. So given the interval we're looking at from 4 to 7, the width of each rectangle is 7 minus 4 on the number of rectangles. And now we can sum the area of each rectangle, which is the width of each rectangle, which we can take out of the sum because it's constant. And then we'll multiply that by the height of each rectangle. So that will be x squared plus 10, or 4 plus the width of each rectangle, multiplied by the index I, squared plus 10. And for the right Riemann sum, we sum from I equals 1 to n. And you can convince yourself that this makes sense by selecting some specific number of rectangles and then calculating the value in the sum and making sure it's equal to the value at the right of each rectangle for those different values of I.